Now we are seeing three curves. Okay, the lowest one is called as saturated vapor curve, the saturated liquid curve, and the topmost is a saturated vapor. So this is a superheated vapor. This is a subcooled liquid. This is a liquid plus vapor. And this is actually supporting. This is called as auxiliary curve. Auxiliary curve. Okay. Now saturated liquid and saturated vapor shows the this is a series of points where we are meeting all the saturated liquid points, and this is all saturated vapor points. So between this saturated liquid and saturated vapor, it is a mixture of liquid as well as the vapor. And now here also you are able to show the five regions. That is, the first one is a subcooled liquid, second is a saturated liquid, and third is a liquid vapor mixture, and 4 is saturated vapor, and 5 is superheated vapor. I am able to show 5 regions in this enthalpy concentration chart, similar to the temperature concentration chart. In temperature concentration chart, there are only one loop only I showed, but here I am showing the difference between there is a gap between the saturated vapor and saturated liquid, because that gap shows the the latent heat of evaporation. For example, x is equal to 0. What is x is equal to 0? This is pure water. Okay, there is no any ammonia traces. This is the latent heat of, I can say latent heat as HFG, latent heat of water. And if the x is equal to 1, that is completely ammonia. This shows the latent heat of, that is HFG of NH3, that is ammonia. So between this latent heat of water and latent heat of ammonia, based on the concentration that may be changing from 0 to 1, then that's latent heat of this mixer will change. According to the change in the mixer, the gap also is varying here. So now, especially for the graphical solution of a state like thermodynamic state or process, there are many processes like adiabatic process, diabatic process, mixing process, throttling, expansion, separation, defligmation, etc. That's a refinement of the concentration, that is the distillation, etc. There are processes are there. After finishing this identification of the state, we can extend this process solutions and then system solutions. System solution. State is a single point, the process is a meeting of 2 points, and system is a combination of the process. Combination, integration of all the process we are calling as system, like power generation system or cooling system, power system, or etc. Now, if I am showing, let us say x is 0.5 is defined, if x is equal to 0.5 is defined, it is easy to take the value of saturated liquid or maybe subcooled liquid also. But subcooled liquid, the temperature is less than the bubble point temperature. This is the bubble point, and this curve is related to the bubble point temperature. This top one is related to the dew point temperature. Okay, and now the between bubble point temperature and dew point temperature, the phase change takes place. Okay, between bubble point temperature and dew point temperature, phase change takes place. So it is starting of the phase change. This is the ending of the phase change with the mixture of x is, let us say example, x is equal to 0.5. And what about the temperature on this vertical line? The temperature is changing, increasing from bubble point temperature to the dew point temperature. The properties that is especially for the enthalpy, straight away you can take the liquid as well as the vapor. This is a vapor, because that is only completely vapor and this is a completely liquid. There is no any issue. But the liquid vapor mixture, yesterday I gave the example also. This liquid vapor mixture has concentration. I can say 3 concentrations. One is a mixture concentration. We may call this as X. One is a liquid concentration, XL. One is a vapor concentration, XV. And also one more, you may define the dryness fraction. Dryness fraction symbol may be pi, because we generally for the steam use X for the dryness fraction, in the BTech thermal engineering, especially solving the thermal power plant. X is denoted for dryness fraction, okay. W is for the wetness fraction, that is opposite of 1 minus dryness fraction is called as a wetness fraction. But now we can't use X for dryness fraction, okay. That's why some other variable, maybe phi, according to the others, I'm selecting phi as a symbol for the dryness fraction. What is the same definition here? Also the same definition. How the dryness fraction is defined here in steam? How the dryness fraction is defined? Mass of the vapor by total mass. Okay. Here also the same definition. Mass of the vapor by the total mass. Mass of the liquid plus mass of the I think edge is over here. Mass of the vapor. Okay, this I am writing here ml plus mv. I have some borders here. The same definition we are using, but here mv, we are calling this as vapor, but this vapor consists of H2O as well as ammonia. The liquid also consists of H2O as well as ammonia. The concentrations are different. Here XV is greater than XL. So there is a relation between XV, X and XL. All the temperatures are same: vapor temperature, mixer temperature and liquid temperature, everything is same, the same temperature. We have to identify this process as a same temperature. So here if you see the enthalpy concentration chart in the graphical solution, apart from this saturated vapor, auxiliary curve and saturated liquid, you can also see the constant temperature lines. The temperatures are constants. I will explain the significance of auxiliary curve later. These are the temperature lines. For example, to identify the subcool, let us say the concentration is defined 0.5, it's showing as 0.5, and P is also given maybe 2 bar, 4 bar, something like this. Okay, the pressure is defined, and given temperature is less than the bubble point temperature, because bubble point temperature or dew point temperature is a function of pressure and concentration. Okay, but single fluid system, saturation temperature is a function of pressure. Okay, just recollect, for the single fluid system, saturation temperature is a function of pressure only. But in this binary fluid system, as per the Gibbs rule, this saturation temperature, bubble point, either bubble point temperature or the dew point temperature is a function of pressure and concentration. I am saying P is equal to bar and X is equal to 0.5. Immediately, either you can calculate or you can read from the graph both the bubble point temperature as well as the dew point temperature. Okay, that's fine. But in case the given temperature is less than the bubble point temperature, we have to identify that corresponding temperature let us say this bubble point temperature is 100 degrees centigrade and given temperature is 80 degrees centigrade. So 80 degrees centigrade, it is a 80 degrees centigrade. This 80 degrees centigrade curve and this 0.4 curve both will meet at one point coincide. That point is a state, given state. That point is a given state where from the graph you can say the state is subcooled liquid. If the given temperature is equal to bubble point temperature, easily you can identify that is a saturated liquid, or dew point temperature means that is a saturated vapor. In case it is more than dew point temperature, you can identify that as a superheated vapor. But the question here is, if the given temperature is between the bubble point temperature and the dew point temperature, how to solve the solution? If the given temperature is, because this is a PTX solution, that means at given pressure, given temperature and given concentration, we are going to read or calculate all the properties like internal energy or enthalpy, entropy, energy, exergy, and so on. Okay, so after identification of all these properties, it's easy to calculate the, let us say, the first law efficiency of the binary vapor system, second law efficiency or exergy efficiency of the so on so poly generation, which is easy to identify. That's why first we are starting with the state. Okay, now my explanation related to this mixer, that is a liquid vapor mixer. If the given temperature is between the bubble point temperature and dew point temperature, how to identify it? So what we can see, see here, you are, I am showing these curves. This is a temperature curves. Okay. Let me take again x is equal to 0.5, x is equal to 0.5. And given temperature is between this bubble point temperature and dew point. Just read this temperature. Okay, I am finding the given. This is the given temperature. This is a given temperature, and at the start the given temperature, that is saturated liquid state. Let me call this as T. Given temperature, and draw a vertical line from this temperature. I am saying from the given temperature. This curve is related to the same pressure. Okay, it is a combination of pressure and temperature, not the concentration. The concentration is related to the axle. Draw a axillary line. Draw a vertical line till the axillary curve. And then once it is touching, draw the horizontal line. So the cutting point of this vertical and this horizontal line is the state, is your state. So here you may call this horizontal line as isotherm.
Sir, can you repeat that? What is the vertical
I
line?
will repeat. Let me complete. Actually, I didn't complete it. I will repeat again. I have some. Okay, right. Okay, this I am calling horizontal line. I am calling as isotherm. Now it is touching the saturated vapor curve at one particular point, and if you are drawing as a vertical line, it is cutting x value. Now you are able to show as XL. This vapor related is called XV, and the mixer is related to X. And this horizontal line is called as isotherm because this is a temperature related to the liquid. You are starting the same temperature. You are showing same temperature line. You are showing as a vapor curve. Now, where you started, you are starting from the saturated liquid. How to identify this point? Again, I am repeating this one. How to identify this point? Okay. read here. Okay, first once you are reading this temperature and compare this temperature with bubble point temperature and dew point temperature. If it is below bubble point temperature, no issue, that is a subcooled. If it is equal to bubble point temperature, that is also no issue, that is a saturated liquid. Equal to dew point temperature, also you are saying that saturated vapor, more than dew point temperature, so that's fine. But if this temperature is between bubble point temperature and dew point temperature, you are deciding that is a liquid vapor mixer. Okay, how to identify this point? This point I am saying, start with the saturated liquid. How to start with saturated liquid? Because this liquid and vapor both are at the same temperature. I am assuming this is a saturated vapor. Yes, really this is a saturated vapor, sorry, saturated liquid, and this top one is a saturated vapor. This is a saturated vapor and this is a saturated liquid. I am identifying the saturated liquid because as per the convenient, there is a temperature curves are available. So take the temperature, this temperature I am saying, where this temperature is lying between the bubble point temperature and dew point temperature. Take this temperature curve and take the corresponding saturated liquid curve and identify a point and draw a vertical line till the axillary curve. That is the significance of this axillary curve. Now what I am saying is why this axillary curve is also included in the graphical solution is these axillary curves are useful to solve the liquid vapor mixer. To solve the liquid vapor mixer. If the state is saturated liquid or saturated vapor or above or below the saturated liquid, there is no use of auxiliary curve. Auxiliary curve is useful only to solve the liquid vapor mixture. That is the significance of this curve. Okay, fine. And draw a vertical line up to this auxiliary curve because that is meant for to identify this point. Then draw a horizontal line. Then draw a horizontal line. Why this horizontal line? To identify the saturated vapor. Okay, you got the saturated vapor. The saturated vapor corresponding concentration is called as XV, and saturated liquid, the corresponding concentration is called as XL. Now to show the process, we have to join these 2 points. Okay, now I will explain the process. For example, the same concept can be explained for the mixing as well as the separation process. Sorry, isotherm. Let me correct this line. This is a mixer. This is a mixture of liquid and vapor. This is called as isotherm. This line is called as isotherm. So, for example, this liquid plus vapor, if you are separating, this is the separator. The liquid is separated and vapor is separated. This inclined line is following the lever rule. This inclined line is following the lever rule. What is the meaning of this lever rule? This is mass of vapor and this is the mass of the liquid. The mass of the vapor is proportional to this mass of vapor is proportional to this length. The length means if I am taking the A, B and C, the mass of the vapor is directly proportional to the length A, B. Okay. And mass of the liquid ml is proportional to the length BC. Similarly, not only mass, and it is also proportionately the enthalpies also. Enthalpy of the vapor and enthalpy of the liquid also you can identify, and concentrations. So if you are making as a triangle here, for example, this is a triangle. This is the height and this is the base. What you can see this triangle, and you may apply the similar triangles otherwise. This triangle can be measured in terms of, let us say, delta H. Y-axis is the y-axis is the delta H, and x-axis is the delta x. X-axis is the delta x. And what are the corresponding formulation here? One is the mass balance for this one, that is m is equal ml plus mv, and enthalpy H is equal HL plus HV. And is there any other? Yeah, concentration also. X is equal XL plus, in case dryness fraction, if you are using XV minus XL. So you may combine all these equations so that you can do the lever rule to solve this mixture of liquid and vapor. Okay, I will show the same properties on the chart. So I have the chart here. This is the enthalpy concentration chart. Before this enthalpy concentration chart, I think yesterday I explained the 5 regions. Actually, in my book, I added this flow chart. I also asked you yesterday if the temperature is equal to bubble point temperature, assign that properties is as what is this property? Liquid mixture. Liquid, saturated liquid, and if it is less than bubble point temperature, this is the subcooled, and equal to dew point temperature, this is a saturated vapor, and the temperature is between the, that means greater than bubble point temperature, and T is less than dew point temperature, this is the liquid vapor mixture. Just now I explained. If the T is greater than dew point temperature, that is called as superheated vapor state. So based on the reading of this input, that is the pressure, temperature and concentration, at the corresponding pressure and concentration, first we have to identify the bubble point temperature and dew point temperature. Then we can compare the given temperature with the bubble point temperature as well as the dew point temperature. Okay, this is the process to identify the regions. Once we are able to identify the regions, it is easy to identify the properties. So now this is a graph we drawn using this MATLAB. X-axis is showing the concentration starting from 0 to 1, whereas the y-axis is a enthalpy, kilos, specific enthalpy, kilojoules per kg. How many curves, set of curves we are seeing here? 3 set of curves we are seeing. One is the saturated liquid, auxiliary curves, and saturated vapor curves. And small letters, I think may be difficult to see the letters. I will read the letters here. The lowest pressure, what here it is showing as 0.2. For 0.2, this is a set of 0.2. Correspondingly, this is a 0.2. Yes, you may see here. This is a 0.2 pressure, and this is the lowest. This is a 0.2. So I can draw here roughly 0.2 liquid and 0.2 auxiliary and 0.2 vapor. Got my point? For one pressure is constant here. You can see how many curves we are seeing for one single pressure: saturated liquid, and saturated vapor and auxiliary. Okay. And similarly, other pressures after 0.2, 0.4, 1, 2, 4, 8, 10, 15, 20. Up to 20 bar it is given. This chart is mostly suitable to solve the cooling systems. Generally, cooling system, the pressure range is 10 bar, 15 bar, maximum 20 bar. But if we are applying using this chart for power generation like Kaliner cycle system, the pressures are more than 20 bar. In power plant, the pressures are more than 20 bar. That's in that case, you may have certain limitation to use this chart. I will supply another chart that is available. The enthalpy concentration chart is available up to 100 bar. So I will show later. Mostly this is designed, even in your textbooks also, the enthalpy concentration charts are mostly designed for the refrigeration purpose only, not for the power plant purpose. Because that Kalina is not yet published in the textbooks. Maybe soon in future, thermodynamics textbooks, you may see the Kalina power plants. But as on today, you can't see any formulations like maybe descriptions nowadays they are coming, but formulations will take time. You are studying very well in advance, actually speaking. This power systems is related to the enthalpy concentration charts as well as the tables. Now, if you are here, for example, the state is here, and anybody, could you start how to solve this problem graphically? Where I have to start? This is a point. And let me take 4 bar, okay? 4 bar. What concentration you want? May I take 0.5?
Yes.
0.5, x is equal to 0.5. But temperature I have to select between the bubble point and dew point. What is the bubble point temperature and dew point temperature at 4 bar? This is 4 bar, okay? At 4 bar and 0.5 concentration. This is okay. This is. And temperature, are you able to read this temperature? 20. This is 200, 50, 40, 20. This is about 20.
Yes, 30.
Okay, 30. Look, this is I'm drawing approximately. It's not exactly, just to demonstrate the point answer. Look, what about the dew point temperature? Dew point temperature means you need some work. Okay, let me take the temperature, sample temperature around 60 degrees centigrade. Okay. I'm taking the temperature is 60 degrees centigrade, assuming this temperature is between bubble point temperature and dew point temperature. Okay, so how to solve this problem? Where I have to start? 60 degrees centigrade, okay? Where is 60 degrees centigrade here? 40, 60. Are you able to see the 60 degrees here? 60, 80, 100, 120.
Yes.
The 60 degrees, where I have to stop this curve? At 4 bar, okay. Where is the 4 bar? This is 4 bar. I have to stop here, okay? Am I correct? I am identifying a point. This is related to 60 degrees centigrade. It is related to 60 degrees centigrade, and pressure is 4 bar. Are you identified this point? 60 degrees centigrade and 4 bar. Okay?
Yes, sir.
Then using scale, because you have to graphical solution, it is not freehand line. You have to use a pencil and a long scale. Long scale, because this is the sheet I am supplying, maybe A3 or A4. Even A4 also, short scale will not be sufficient. You have to use the long scale. Okay, but I can't use a scale here. Just a freehand line I am drawing here. Where I have to stop? I have to stop at 4 bar, okay? 4 bar is 60 bar. This is 4 bar. Yes. Got it? Hello? This is, I am stopping at the axillary curve. I am stopping at the axillary. After reaching this axillary curve, what we have to do? We have to draw a horizontal line. We have to draw a horizontal line. Where I have to stop here? It is very close. The saturated vapor curves are too close. 0.2, 0.4, 1, 2, 4. I think this is the curve. I can see. It's at higher concentration, almost more closeness is coming. It's I can say approximately 99%. Ammonia concentration is 99%. Then what we have to do? Okay, I identified the 3 points: saturated liquid. This is the point on the auxiliary curve, and saturated vapor. What I have to do now? What I have to do? This is a line at 0.4. The join the saturated liquid, XL, and this is XL. Join these 2 points again using scale, using long scale. Join these 2 points. Got it? This is called as isotherm. Temperature is constant. This is the temperature of liquid, and this is the temperature of vapor, and this is the state where the 0.5 concentration line and isotherm both are meeting. This is your state. That means liquid and vapor state. This is liquid and vapor state. Okay, to identify this point, we have to start from the saturated liquid and end with the saturated vapor via auxiliary point. Now, in the graphical method, XL can be read directly. It is around 0. Sorry, please. Hello. Yes, sir. Could after half an hour, I'm in class, sorry. I'm in online class. Yes. Okay. Sorry. What you can read from this graph, XL can be, you can take the XL value, it's less than 0.5, it's around 0.335, etc. And HL can be, you can take the value of HL, and similarly XV and HL, you can get the HL, HV, XL, XV. Okay. Yes. We have 5 minutes time. I will give you a small task to you. Could you combine the mass balance and the energy balance equation here? M is equal to ml plus mv. Okay. And H is equal, this is a H, okay. H is equal HL plus HB we can't call, I think so, because this is the dryness fraction. HL minus, where its dryness fraction is equal mb by ml plus. Could you combine this equation 1, 2, 3? Replace this phi by this mb by ml plus. Could you solve? Just take 2-3 minutes time. And I want one value. What I can give me a simplify here. Yeah, simplify H. Simplify H. That's all. In terms of mass and enthalpy. Okay, could you solve it? Are you understood? Hello?
So we have to convert H in the form of
No, replace 5 by m. Replace 5 by m. H is equal to HL plus pi into HV minus HL, okay? Sorry, HV minus HL. I've replaced pi by MV by ML plus MV. That's equal to HL plus MV by ML plus MV. What is ML plus MV? That is M.
M.
Yeah, that is M, total mass. HV minus HL. Now, H minus HL is equal MV by M HV minus HL. Okay? Or H minus HL by HV minus HL is equal MV by M. Okay, see here H minus HL. What is the distance of H minus HL? H and HL. This line, okay?
Delta H.
Delta H. This is a delta H. Delta H you may simplify for HV minus H or H minus HL. This length you are getting. This length you are getting. What is the total length? HV and HL. Total length in terms of enthalpy I am saying the y-axis HV minus HL, and this length is in y-axis H minus HL. And what about the mass? MV and M. You are showing this is MV. What is this length you are showing? This length is towards the liquid side. Okay. This length is towards the liquid side, but what mass you are showing in the equation? Towards the vapor mass. Have you simplified the equation? H minus HL by HV minus HL is equal to MV by M. Okay. Have you got this simplification?
Yes, sir.
Okay. Now what I am saying is H minus HL, this is the opposite side of the vapor line. If I am calling HV minus, this is HV minus H. HV minus H, you will get HL here because MV can be replaced by M minus ML, or ML can be replaced by M minus MV. Because here I expressed MV by M, okay. The same can be expressed ML by M also. Because that is a M minus, you have to again write this equation, simplify this equation. Now at this instant of simplification, what I am saying is H minus HL, this length is proportional to the opposite side mass. And also, could you add concentration? Similarly, concentration also. What about the concentration here? What is the relation of concentration? What is the relation between X, XL and XV? What is the relation between X, XL and XV? X is equal to XL plus pi into XV minus XL. Is it correct? Same like enthalpy. Hello?
Yes, sir.
X is equal to XL plus pi into XV minus XL. So if you are simplifying, In place of enthalpy, you will get, here I am writing H minus HL, okay. You will get X minus XL by XV minus XL is equal to MV by M is equal to MV by M. This is the y-axis relationship you are showing. This is the x-axis relationship you are showing. That means this length corresponding to the enthalpy is directly proportional to the vapor side length. This is called as lever opposite side. Even iron carbon diagram in metallurgy or material science subject, iron carbon diagram also that is what the mixture ferrous carbon. Okay, I think so. Long back we studied this iron carbon diagram. So using the lever rule, you are able to calculate the carbon percentage. That's why you define low carbon, medium carbon, high carbon. Are you recollected that lever rule?
Yes, sir.
Same here also same. We are also applying the same lever rule. That's A plus B. There are a liquid the A plus B we are applying, and based on this lever rule we are solving the process. Now may I continue next class? Process.
Okay, sir.
These explanation you may refer the textbooks, refrigeration and air conditioning. Maybe one I referred the material. One is IIT Kharagpur. PDF files are available in internet. That's free material. If you Google IIT Kharagpur, these are given by lessons by lessons. There are 30-40 lessons are there. This is a binary fluid mixer. The title is ammonia vapor mixer, I think so. Thermodynamic properties or something like this. If you are typing with IIT Kharagpur, you can download the PDF files. That's nice material. Or in terms of textbooks, there is one book Manohar Prasad. You also might be referred in bachelor's time to BTech in refrigeration and air conditioning. Dr. Manohar Prasad, refrigeration and air conditioning by Manohar Prasad. Are you aware of that book? Manohar Prasad.
No, sir.
Yeah, that's a famous book actually in Indian order. It's a nice book. If it is available maybe online or offline, just to refer that material so that we can understand easily. Either IIT Kharagpur or come both Manohar Prasad. Manohar Prasad, there is one more book, refrigeration and air conditioning tables also is available. Properties also is available. Charts as well as the tables for all the refrigerants. As well as this, what charts I explained just now, the concentration chart. This is also available. Of course, I will share some of the material in my books. Okay, next class means next week. Okay.
Yes, sir.
Yes.
Yes, sir.
Do you have any questions now? Before taking attendance. Next week I will explain the again lever rule, because same lever rule again it is coming for the process, like separation process, mixing process. Again we have to combine these mass balance, energy balance, etc. That time I will explain again the Dreyer's fraction. Okay.
Yes, sir.
Do you have any questions now? Hello?
No, sir. Not yet.
Number 2. Akshay.
Present, sir.
3,
Present, sir.
4. Avnish. Manoj.
Present, sir.
Deepak.
Yes, sir.
Dahit,
Yes, sir.
Sophia Das,
Yes, sir.
Sukesh,
Sir, roll number 4.
Swapnil,
Present, sir.
oh, Avnish आया,
Yes, yes, sir.
Vaibhav,
Present, sir.
Yuvraj,
Yes, sir.
Mitra,
Yes, sir.
Mitra.
Present, sir.
Okay, bye. We will meet next week. Tomorrow I have some meetings. That's why tomorrow I'm not coming. Just 1 minute may take regarding the independence study. May take 1 minute time.
Okay, sir.
1 minute, please. Recently, we arranged one meeting with the head of the department to get the guidelines for independent study. Because in the syllabus there is no proper guidelines, regulations. That's why after the meeting, I want to share the outcomes of the meeting. Just stay for 1 minute. All are here, I think so.
Yes, sir.
Okay.
Yes.
Now, I opened the file. Are you able to see the file?
Yes,
Yes,
sir.
sir.
Okay. This is a minutes regarding to our independent study. We framed some guidelines. As per the discussion, we framed some guidelines. Earlier, it is actually similar type of independent study. Now, as per our discussion, I want to share the what we have to follow for independent study. The first one is soft computing technique must be learned by all the students. See, this independent study, the name itself is saying we have to equip with the skills. We have to equip with the skills. So instead of solving a separate problem or separate mini project or mini project, what we are assuming is what already you engage with the projects, okay? So what are the efforts or our inputs you may apply to solve your project? So you will get the two benefits. One is you can see some progress of your final project, the capstone project, as well as this carries the 3 credits. The independent study carries the 3 credits. Is more weightage is there actually. Almost it's equivalent to one subject. 3 credits means equivalent to one subject. That's why we can't neglect this one. You have to, every one of you has to equip with the skills. Any skills, it's not like the fixed skill. That's independent. You are independent based on your interest, based on your suitability to your project problem. You select the skills. This is mostly what type of skill it is. It's a soft computing technique skills. Soft computing technique skills. The new technique may be optimization techniques. Mostly we will prefer the optimization. I also stressed one of my presentation the need of optimization. Just by finding the workable solution, it's not sufficient. It's should be optimum system. So optimization techniques, Simulink methods like examples. These are examples like MATLAB, machine learning, CFD, artificial intelligence, technical coding, graph theory, ANSYS, CAD/CAM, Abacus, SolidWorks. I can list many such skills which is useful to design, optimize the planned engineering product or the process. A thesis supervisor will monitor the above technique for his students. So supervisor also has to attend in the online meeting. I created the online meeting. Soon we will share the schedule. Dr. Sanjay is preparing the schedule. According to the schedule means we have the timetable. The schedule is prepared in the timetable slots now. A monthly report must be submitted through the thesis supervisor to the course coordinator. That means supervisor has to sign That scanned copy you have to upload in the Google Classroom. The evaluation of the report and presentation will be 3 times in the semester. We are evaluating 3 times. Maybe level 1, level 2, level 3. And the level 1, what our expectations, 2, 3. That also we will soon we will share to you. But be ready instead of waiting to our instructions, because we are framing the instructions now. Now itself you may get ready, you may start, because already objectives are defined for you, project objectives are defined for you. You may go through the objectives and identify the suitable methodology and suitable techniques and have a discussion with your guide and get ready with some of the solutions and some groundwork, planning, literature and history and identification of the methodology, etc. Are you clear some of our expectations from this independent study?
Yes, sir.
Yes.
Sir, if I'm working on my project on MATLAB itself, so I don't have to do anything different now for this.
Yeah, that MATLAB you are solving according to your guidelines of the supervisor. That's fine. But
Yes.
we will in your presentation we will give along with your supervisor, Dr. Sanjay and myself also. We will monitor whether what are the techniques you are doing, that's sufficient or not. Okay, that we will monitor. Some follow up will be there. So you can see you also will get benefit of more inputs and some sort of
Feedback.
positive progress you can
Yes.
expect. Instead of, for instance, nobody is watching me, so how we won't do much. It's like human psychology. I'm saying, if some monitoring is there, you may do in a better way. Yes, ma'am. Whatever the MATLAB you are doing, that's sufficient. But we will give whether it is online or not. We will see.
Okay, sir.
Any else? Because you may have plenty of doubts, so let me know, because based on accordingly we may modify our speech accordingly, the regulations. Is it fine or you are feeling some burden?
No, sir, it's fine, sir.
Yes. It's good also, because tomorrow industry, the subject knowledge may be minor. The skill capability is major. They will see mainly what you can do. What you study, that is common to most of the students. Knowledge is common to all, but extra features are skills only. Yeah, you may have some doubts. May I know what doubts you have? Soon we will schedule the meetings. Dr. Sanjay is preparing. I will share this file in Google Class. You have any questions, Deepak? I think whether your objectives are framed clearly, still under process. So that's why if any pending is there with the projects, now itself online you will meet your project guides and define the problem solutions objectives clearly at the now itself you may define the objectives. Okay, Manoj, it is fine.
Yes, sir.
Mapriya Das, is it okay?
Yes, sir.
Okay. Be ready soon. We will call all of you. Okay, fine. Bye. Right. Bye. I'm leaving the meeting.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Okay.